Welcome everyone to my study presentation. My name is Fernando Moreno Jabato, and I'm here today to talk about my work named Kernel-based approaches to identify hidden connections in gene networks using NetAnalyzer. Before I start, I hope everyone are fine regarding the current COVID situation. Also, I want to thank my research team, led by Juan Antonio García Ranea, and with my teammates, Dr. Pedro Seoane, Dr. Elena Rojano, Dr. Jean Perkins, and PhD student Jose Cordova. Having said that, let's start with the presentation. This presentation is structured in three main parts. At the beginning, we will talk about what a kernel is and how and which ones we have implemented. After that, a benchmarking of our implementations will be discussed. At the end, we will show a practical application with a disease-related genes network. A kernel function can be mathematically defined as the inner product between vectors of a given Hilbert space, which does not necessarily perform a transformation of this space. A kernel function must be continuous, symmetric, and semi-definite. This third property is not strictly mandatory, but the usage of a positive definite kernels ensures the convergence and unique solution for kernel-based mathematical methods which will be performed. But what does it mean? What it really means is that we can apply a mathematical function over a set of elements placed in a space like this, and obtain a new perspective of these elements like this other. Choosing the correct operations, we can perform this dimensional change in order to obtain a better data distribution to perform clustering or other analysis tasks. These kernel operations have become very popular because of their advantages for machine learning operations, especially if we take a look at a similarity function definition. As we can see, a kernel operation can be used as a similarity function. When it's used to transform a network adjacency matrix, we obtain a new matrix which values can be used as similarity between network elements. Once we have explained what a kernel is and its utilities, we can go through kernels implemented for this study. For this work, we have implemented 4 different kernels. First of all is kernelized adjacency matrix, which consists in a simple kernel which only affects to matrix main diagonal. Second one is called Laplacian exponential diffusion kernel, which uses the exponential of a weighted Laplacian matrix. Third kernel is an application of Moore-Penrose pseudo-inverse of the Laplacian matrix, which is called common time kernel. And finally, the fourth one is an alteration of the exponential diffusion kernel called Markov exponential diffusion kernel. All of them have been implemented in 4 different languages, which are MATLAB, R, Ruby, and Python. I take the opportunity to indicate that all implementations are available in a public GitHub repository. All kernels have been tested using random binary and weighted adjacency matrices, with natural values between 0 and 100. Matrices sizes has been 2000, 5000, 10,000 and 15,000. To orchestrate all pipelines, Workflow Manager Autoflow has been used, and to measure resource consumption and performance, executions have been run into specific machines, which specifications are being shown in your screen. Finally, a maximum time has been applied in order to kill executions which exceed inadmissible time, which has been fixed on 24 hours. Main features measured have been execution time, CPU usage, memory usage, and error rates comparing each result against others. This plot shows error rate obtained for all experiments performed. To understand this figure, we must know that each graph portion corresponds to one kernel operation. After that, each ring is assigned to one programming language, and per each of these rings, 4 other inner rings are being plotted corresponding to each matrix sizes. Finally, all programming languages have been placed again as spokes, and intersections finally contains a heat plot with error value obtained. In this case, error rate has been represented in logarithmic scale. If we take a look to these results, we can observe that there are gray regions which corresponds to error implementation that have been killed for exceed execution time thresholds. Now, inspecting correct results, we observe that we obtain low error rates for Markov exponential, commute time, and exponential Laplacian kernels respectively. Not the same for kernelized adjacency matrix, which obtains high error rates, something expectable taking into account the simplicity of the operation. For this measure, no relevant differences are observed between programming languages. With error rates controlled, we also measure time, CPU, and memory consumption. Focusing on time graph, we do not observe relevant differences between languages, except for R language, which obtains high execution times, getting to provoke launch endings. First differences between rest of languages are found at memory consumption, where Python shows greater usage than MATLAB, and Ruby reaches significant usage respect to others. We have inspected this significant usage, and we have found some improvement points in matrix operation performed in order to avoid some matrix replicates which launch memory consumption at big sizes. Note that better usage of memory performed by MATLAB is not a surprise because of its mathematical orientation. Finally, CPU usage has been monitored in order to inspect multi-core behaviors of each implementation. Note that a value greater than 100 means that more than one CPU is being used. At this point, we clearly observe a better performance of Python and Ruby, which becomes significant at higher sizes. This behavior can make a significant difference for huge networks, which contain several thousand of elements, like biological networks have. In summary, we have observed a good performance of MATLAB, Python, and Ruby for all kernel types. R has shown big time consumptions for high matrix sizes, but contains correct results for small ones. Inspecting resources consumption, we can conclude that Python and Ruby offer best performances, especially for big matrices, which corresponds to real-world data networks. Now it's time to apply this implementation in a real biological problem. As we have commented, kernels have become very popular in data analysis fields, especially for machine learning algorithms. For this study, we have applied kernels to prioritize disease-related genes to find new relations which are not being observed yet. This methodology is described at Zampieri et al. Previous work. Most specifically, the problem is the following. We have a network of genes related by their significance on already studied diseases. In future studies, new relations will be discovered and network will mutate. Our goal is to predict these potential new relations in order to find candidates and help to design future studies. To do that, we have used Borningen et al. Dataset. This dataset is composed of known gene-disease relations at a given time, taken from various diseases database. An additional 42 novel genes which were found to be related to these diseases during the subsequent 6 months. We used these 42 new genes-disease relations to compare the performance of these different kernels. To do that, we use already known genes as seeds. Related genes are ranked, and top of these ranks are checked in order to find these 42 expected genes. As input adjacency matrix, we compute a matrix based on string database version 8.2, which are previous to these 42 new genes discovering. This generates a matrix of over 17,000 elements. After that, some measures have been checked. First of them is the matrix values after transformation. As you can observe, kernel application generates several non-zero relations which enrich the network. These new relations can be cleaned applying a threshold. In this case, we have not applied a cut because we are going to study ranked list, which will remove spurious relations. After that, seeds are used to generate linked lists and the following accurate results. You can observe the following metrics: median and mean, which corresponds to the position of 42 elements in ranked lists; lowest, which is the worst position obtained at percentiles of the ranked list; true positive rate at different thresholds, which corresponds with the percentage of found target genes queuing at percentile specified; and finally the area under ROC curve calculated as Ampieri specifies. Checking this table, we can observe kernelized adjacency matrix obtains acceptable results, which indicates that our datasets contains enough information to predict our target genes. Exponential Laplacian is destroying this data predisposition to target predictions, but rest of kernel types are improving base results, being commute time, which offer best performance for this problem. Finally, the conclusions of this study are: kernel operations can be implemented in several platforms, including ones which are not designed for mathematical or statistical purposes like Ruby. Different languages can offer different performance, which can affect to your studies depending on the magnitude of your problem. Kernels can be applied to real datasets, obtaining interesting results without necessarily applying complex algorithms or machine learning. As future works, we propose the fixing of performance problems observed for some platforms at time and memory consumption. Perform new studies for different problems, especially with more topology networks variety, in order to identify which kernels works better for each network type. Implement more kernel algorithms to offer more options for more problems variety. And this is the end. I hope you have enjoyed my presentation, and I invite you to send your question to my email or ResearchGate profile. Thanks for watching and have a nice day.